think it's 5, say to be fixed. I compute the p-adic valuation of that number, that sequence, and I ask, is this sequence now the p-adic valuation of all the Stirling numbers of the second kind? Is that independent of n? The answer is no. You check. You compute the first few, and they have different values. So if that is the case, then what you do is you do a binary split. So this represents n. So you take one vertex representing 2n, the other vertex represents 2n minus 1. And you do the same thing. You ask, at each vertex, you ask the question, is the p-adic valuation of that vertex independent of n? So for example, the vertex on the left will represent now the p-adic valuation of S2n, 5. Is that independent of n? The answer is no. It's easy to check that something is not independent of n. You compute the first few and you get something different. Right? And then you split again, there. And you continue playing this game. So you're forming this binary tree. Right? There's another one. Oh, there. At this point, you find that the answer to the question that we've been asking at each vertex, the answer is positive. In other words, this vertex has all p-adic valuation equal to 0. In other words, the p-adic valuation of S4n minus 2, 5 is equal to 0, independent of n. I declare that to be a terminal vertex. And then you do this one here, that splits, that's terminal. And now you continue the game. That terminal, that splits, that's terminal. So that's what you get. So what you observe is that you're going binary, you're doubling the number of vertices up to a certain point, and then on each row, half of the vertices are terminal, half of the vertices split. Same thing true here. So for example, to draw the next level, 2 of these will be terminal, and 2 of these will continue. I can prove that for 5, and only 5. My proof does not work for 6. So if I replace Sn, 6, that's an open problem. So I've conjectured that Smk, for any k fixed, what you get is a binary tree after a while, after a certain point. I can tell you exactly where it stops, and then the number of vertices remain constant. So that we have tried to prove, extend the proof. The proof that we have for k equal 5 simply does not work from this point on. I became convinced that it's not a matter of adjusting the method, it would just not work. Need a new idea. So that's a conjecture. Okay. So I have a feeling that, you see, when you do this motion here, when you start doing the splitting, if you want to go all the way to infinity, you move here, you move to the right, then you move to the left, say you move to the left here. So at each level, what you're doing is you're moving either left or right. That's my conjecture. So that creates a random walk. And I think that, and I don't know how to justify this, I think that properties of that random walk will determine whether those pictures that I showed you before are pretty or not. So that's a very vague statement, but that's all I can say. Okay, someone said every dog must contain a proof. I say every dog must contain an integral. But I'm sorry, I think I'm going to show you the last part, so because of time, I will skip this. This is an integral that we played around for a long time, and we now understand completely these numbers for any, not for any prime, for p equal 2. I understand them completely for p equal 2. Odd primes are more difficult. There are some, well, this is a combinatoric seminar sometimes, so here is a list of combinatoric statements. The sequence is unimodal that I proved with my former student, George Boros, in 2001. It took a while to prove that actually the log concave, this is Manuela and Peter at Risk, 2009. There's no human proof of this statement, but that's okay. There's a two-log concave proof by Bill Chen and his students that's going to appear next year. And I've conjectured that these are infinite log concave, this sequence. So if you want to know more about this, I'll talk to you later. This is what the pictures are. So you see, when you see these pictures, if you're not in an optimistic mood, then you realize that it's going to be hard to get explicit representations of these pictures in any other way, right? Either by a formula or by a binary tree construction and so on. And I was very surprised actually when we were able to finish completely a binary tree description of pictures like this. So there's a binary tree that encodes these formulas completely. And I play the same game that I described from the Stirling numbers. I do exactly the same, right? The question that you ask is a little bit modified. You don't ask whether the p-adic valuation is constant. You ask whether the p-adic valuation is a multiple of n, or something like that. Some small variation, but the idea is the same. What is remarkable here is that for these numbers, this generates a finite tree. We can prove that independent of n, all these pictures correspond to finite trees. Right? There's an example. And these numbers, I can give you explicit formula. Well, I can't right now, but we have explicit formula for these numbers. And out of these numbers, you get a formula. So that's the complete cycle that I wanted. You start with some experiments, you look at some data, you look horrible, and then you generate a tree, and out of that tree you get a formula. So here's a formula for these numbers, right? That are explicit. These are the kind of things that I feel comfortable with. A formula that I can do with. Trees are mysterious to me. Okay? Of course, this opened the interesting question now is this, right? So here you have the Stirling number satisfies a nice recurrence. You have these numbers DLN that also satisfies a nice recurrences, the non-constant coefficients. Some of them have infinite trees, some of them don't. What makes them work? What makes the Stirling numbers continue going forever in this tree and this one have a finite tree? There has to be a reason. We just have to find it. We don't know yet. Okay, here's what I want to show you. I have exactly plenty of time. Okay, so here's an nonlinear recurrence. Okay, xn is n plus xn minus 1 over 1 minus n xn minus 1. If you stare at this for a while, then you will know where it comes from, right? I'll tell you. If you look at the monthly or any of these journals, many times you see formulas like this, evaluate this. Well, the answer is easy now, you just type it into Mathematica or Maple, it comes out. Right? But all the proofs that we knew about this type of formulas came essentially out of some telescoping. You have to rewrite the term in some way that telescopes, right? Something cancels and all. So a while ago we tried to, I kept on getting more and more annoyed because you get seeing the same problems coming in different papers. So I said, okay, let's write a short survey paper on all the techniques that have been used for this type of problems. So we did that, and then I thought maybe the finite sum is much more fun than the infinite one. Right? Finite objects tend to be much more complicated than infinite objects, and they're usually much richer. Right? So I look at the sum of angles. I violently replace the 2 over k squared by k because to make the problem simpler. And I look at the sum of angles, and to make it into a number, I compute the tangent again. And the addition theorem for the tangent gives you the recurrence. That's what I thought. And now that we have this problem, you play with it, right? That's the recurrence again. Here's the first few values. Starts at 0. You get 0, 1, minus 3, 0, 4. That's not what you expect, right? Because if you have this recurrence, you have this fraction here for a reason. So you should not get integers. This is not fair. You should get fractions, like that. Now, this is what you should expect. So after 4, you get like this. That's what you expect. So, questions, right? I tend to like to finish papers with a question because if the person has the trouble of reading everything you do, at the end you should tell them what you don't know so that the person continue writing to you something. So we figured out what should be a nice question for this. I figured, okay, what is this 0 doing there? So the first question was, is xn 0 again? Right? Do you get 0 again? That was I could have asked you get -3 again, but that would be a dumb question. 0 is an interesting number. So, and the other question that we ask is this thing ever an integer again? So the first question we answer using valuations. The second one is still open. And I want to show you, I won't tell you too much about how we answer this question.
Yes or no?
Huh?
What's the answer?
To 1?
Yeah.
The answer is never again. Never again. How do you prove? Here's a question for you. How do you prove that a number is not 0? You prove that for some prime, the p-adic valuation of the number is finite. That's it. Right? That's what we prove. The duality valuation of these numbers is either 0, meaning the number is odd, or it has this formula. Right? So it's always finite. So the number cannot be 0. That's the end. It took us a while to figure this out, of course, but that's the conclusion. Right? Okay, here's the picture of the sequence. The integer part, so let me write down.
Is it obvious that you never divide? Is it obvious that you never divide by 0? So
Yeah, you have to, yeah. So the recurrence is this. So if I want to prove that something is not an integer, what I'll have to look at is the integer part. So what I have to show you is that these dots are never here. This is 4, I think. Right there is where it's 0. That's what you get for the first 500 numbers. This is the fractional part of these numbers. Okay, so 500. This is 1,000. By the way, this is a discrete picture, okay? So these lines, of which I know nothing about, they are formed by the sequence, by themselves. Right? If you really zoom in, you will see the spaces there. If you put the dots much smaller, where you can see them, you can see that it's a discrete graph. Right? So there's only one point here. There's no crossing here. That's 3,000. That's 50,000. Now you see, you can forget completely about where the problem came from. Huh?
That's the closest integer, that's the fractional part.
This is a fractional part, right? So my conjecture is that this curve never touches, these pictures never touch the horizontal axis. Now this is a much cooler problem. Because I have no idea about this problem. I call this the granular regions. And then these are these curves. There's some kind of interaction here in the middle. What is interesting, if you do the same graph and you graph every other point, then you get exactly the same structure. But these curves do not get into the granular regions. There's a separation. Yeah?
What is happening when these lines are overlapping?
They don't.
But I mean, is it like every other number is on one, like, say, like the
No, they go up and down. The line form in a very strange way.
So it's like every.
Yeah, this point here, the next one will go up there and come back and then form these lines. Yeah.
Does it alternate perfectly?
No, no. I would have told you. I would have known something. No, I have no idea. I don't know. There's a very beautiful book, by the way, online by a guy named Oliver Neal at Harvard, a book on probability. And if you look in the last chapter, has some kind of selected topics. There's a picture that looks very similar to this one. That gives me hope that something I might be able to do. But the picture is really cool. By the way, this continues repeating. I did to sort of, I ran over the weekend until my laptop was hot. And the picture remained. These regions continue reappearing. The width don't obey any law that I know, so it's a good problem.
So it's like a chaotic.
I don't like that word.
Yeah.
Chaotic means you don't understand what's going on. No. Okay.
They get very close to 0 once in a while?
Yeah, the dense is 0, 1. That's my conjecture. Okay. Here's a related question. When you try to prove something out of your sequence, right? So here's a theorem. So you look at the product from 1, I won't tell you how we thought of this, took us a while, from 1 to n of 1 plus k squared. If this is a square, then xn is not an integer. We're very proud of the theorem. Appeared in a paper in a prestigious journal, 2008. This is a really bad result. You know it's a bad result when the paper that solves your question appears in the same volume of the journal. It's a square only for n equal 3. So it's a good theorem. It took us a while to prove it, but it's useless. So, new approach. And with this I'll finish. I have exactly 4 minutes. I'll speed up. Here's a new approach. You take that sequence, you define un to be the denominators. If they're not integers, that implies xn is not an integer. Because if xn were to be an integer, there has to be an integer. You define a new sequence like this. You start with f1 equal 1, and then you multiply by these uns to form the next f. Okay? So look, I don't know if these guys are integers, so what I'm doing is doing rational arithmetic. These uns are, in general, not integers, so the fn's are not going to be integers. There's the recurrence for the fn's. The recurrence with non-constant coefficients. Okay? And from here, I can prove that they're integers. Okay? If I were to lie in front of you, I would say I had a good idea. No. What I did was I compute the first fn, the first 10. I went to Sloan, and I knew where they were. I knew what the numbers were because I found them in a different place, but Sloan confirmed that these are the right numbers. Once you see that these are the right numbers, then you know how to prove this recurrence. And the recurrence will give you automatically they're integers. It takes some time, but they are integers. It's fn's.
It's not obvious.
Huh?
You divide by -1. It's not completely obvious.
Is what?
The recurrent does not imply immediately that
No.
integers.
No, because there's a coefficient in front.
I know. So
Yeah.
So you have to do something.
Ah, yeah, absolutely. You have to do something. That's why it's called a theorem. Okay, here we go. This is like this, and these are the uns, right? They're integers. Okay, here's how I'm going to prove my conjecture. I'm going to show you that for each n, there's a prime, p sub n, such that this prime divides this guy and not that one. Yeah, that will prove that uns are not integers, right? If something that divides the denominator doesn't divide the top, that I can understand. Notice the emphasis on the phrase is on the word will, that indicates future tense. Okay, here's how I do. So, okay, what do I have to do? I need to study primes that divide one term and not the next one. So I need to look at these graphs and see. So I'll go back to the beginning. I look at graphs of valuations of the fn's. Okay. And I have to show you that there's a dip in the graph, right? That the power that divides the left is more than the one that divides the right. So I have to look at graphs that I observe something going down. That's what I want to do, essentially. Oops, there. Right? So this statement here can be translated after you think of for a minute that you have to observe some part of the graph that is decreasing. So p equal 2 will not help me because the graph is monotone. P equal 3 will not help me because it doesn't appear. The prime 3 doesn't divide these numbers. Prime 5, okay, there is some monotonicity going here. These are the kind of thing that helps me. But that's too fine. I'm going to have to work too hard. If I want to use the lack of monotonicity for this prime 5 is going to too much work because this is too fine of a structure here, right? I need to understand too much about the graph. So 5 is not good either. 7 doesn't help because it doesn't divide. 11 doesn't divide. 13, again, too much fine structure. 19, that's the one I want to work. Okay? So 19 is the prime that you have to work. This is hopeful. More data. That's what it looks like. So this is starting to look like pictures that I can understand. There are the spikes here, 2 spikes repeat, then there's a bigger spike and so on. So this gives me hope. There's the next one. Oops. Other hopeful primes apart from 19 are 43, 71, 79. It doesn't appear in Sloan. The only thing I know is that these are the ones that look like that. So now the immediate plans are to analyze the recurrence modulo 19. And the theorem will say there are infinitely many n's for which xn is not an integer. We shall see. Thanks. 5:49.
Victor, we can to answer questions in private. Thank you.